All right, so before we talk about the radius and intervals of convergence, let's first remember how to use the ratio test to find whether a function or whether a series converges or diverges. So remember, you're finding the limit as n approaches infinity of the absolute value of n plus 1 plugged in, so that'll be n plus 1 squared, and then 2 to the n plus 1 over 3 to the n plus 1 times the reciprocal of this, so 3 to the n over n squared, and then 2 to the n plus 1. And then remember, our goal is to cancel out as much as you possibly can, so we're going to rewrite some of this. So we get the limit as n approaches infinity of the absolute value of n plus 1 squared, and then 2 to the n plus 1 times 2, right, because we've got that extra 1, times 3 to the n, over 3 to the n times 3 times n squared times 2 to the n plus 1. Then we cancel whatever we can. So in this case, it's going to be 2 to the n plus 1, 3 to the n. That's it. So we can rewrite this as the limit as n approaches infinity of, let's see, 2n plus 1 squared over 3n squared. Well, this is same degree divide coefficients because there's an n squared in the numerator and in the denominator. So this would end up being 2/3, which is less than 1, so it converges. Now, in this example, we were able to find the exact series that converged because we knew that that value, when we found the ratio, was going to be less than 1. But what if it was just similar, right? What if this number right here, that 2, what if it wasn't a 2? What if it was a 1 or a 3 or a 10? Would that be enough to change what's going on here? Well, the answer is yes. So we're interested in not only determining if a specific series converges, but we also want to understand more generally what has to happen in order for a series to converge. So if we change that 2 to an x, right, we knew that it converged when it was 2. But are there specific values where it would converge versus not converging, right? Could we find, if there are, can we find that interval? And then how? Well, there's a couple of things that we need to know. And instead of just trying values, we can actually use the ratio test to determine these values because there is a limited range of numbers that will allow this to converge potentially, right? It depends on what's going on in the equation. So first, just things to know, every series has a center. Okay, this is the value that makes every term of the series 0, so no matter what, and it's trivial because everything will be equal to 0. Now, having said that, since they're centered at 0, we need to find the radius around 0, right? So in both directions, what values will make this converge and what values will make it diverge? So this interval that I'm talking about, those numbers that we can go to, that's the interval of convergence. And then, of course, just like a circle, right, the distance from the center to your endpoint, or the border, is going to be your radius of convergence. And we are going to use the ratio test to help determine this interval of convergence. But we do end up needing to go a little bit further, right, to find the specific endpoints to see if those are included or not included. Okay, so we're talking about a whole interval where this series would end up converging. Okay, and we're going to find all of the values, not just one, not just guess and check, where we have a strategy and we will use that strategy. So here's what we do. So we're going to determine the interval and radius of convergence of this series and we just kind of did it when we talked about finding it for 2, right? We found it for where x was 2. Now we're going to find it in all circumstances, every single situation that you could come across. What numbers will make this particular looking series converge. And notice, there's an x here, right? And that's going to give us those values that we're looking for. That's why this is a little bit different, because we're not just talking about a number raised to the power of n plus 1. We're talking about x raised to the power of n plus 1. So we're trying to find those x values that make this true. So the first thing we do is we're going to use the ratio test, right? We're going to say, well, if I have the limit as n approaches infinity, we're still plugging in n plus 1, right? That hasn't changed. So I'm going to plug in n plus 1 everywhere I see n, so we'll have n plus 1 squared, x to the n plus 1, and 3 to the n plus 1. And again, multiplying by the reciprocal, so 3 to the n squared, x to the n plus 1. And we did just do this problem in that first example. So we're splitting it up, right? The n plus 1 squared doesn't change. X to the n plus 1, if I want to cancel it with the denominator, needs to be x to the n plus 1 times x. And then 3 to the n stays 3 to the n. In order for 3 to the n plus 1 to cancel the 3 to the n, we'll need 3 to the n times 3. And then n squared, and then x to the n plus 1. Now we cancel what we can, so that'll be the x to the n plus 1 and 3 to the n. So we're left with the limit as n approaches infinity of n plus 1 squared times x over 3n squared. Now here's the thing. We are finding the limit as n approaches infinity, not x. So technically, we don't need the x or the 3 to be anywhere in this equation, right? We're actually going to take the x and the 3 because they don't have n's, right? So we're going to take those and we're going to pull them out front. So we're going to say that this is equal to the absolute value of x over 3, right? Pulling it out, leaving everything else inside, of n plus 1 squared over n squared. Now we know, and this is multiplication, by the way, like all that's multiplication. Now we know that we can find the limit as n approaches infinity of n plus 1 squared over n squared. Again, I can pull out x over 3 because there's no n in either of them. Okay, you can only pull things out that doesn't directly correlate with n. But I know that because this is same degree divide coefficients, just like in that first example that we did, it's going to be the ratio. Well, the ratio here is 1 and 1. So that's just 1. So we actually end up, that all goes to 1. And we're just left with the absolute value of x over 3. So that's the result of the ratio test, right? Is this absolute value of x over 3. Now, according to the ratio test, in order for something to converge, that value, that limit that we get, has to be less than 1. So that means that the absolute value of x over 3 has to be less than 1 to converge. Well, if it has to be less than 1, the absolute value has to be less than 1, then really negative 1, x over 3 would be between negative 1 and 1, right? Mathematically speaking, those are equivalent statements. And then to make it even more equivalent, where we have whole numbers, x would have to be between negative 3 and 3. So right now, our interval is from negative 3 to 3. That means that any number x, that we plug into this equation right here would have to be between negative 3 and 3 to converge. But any of them do. However, right, so we've got this statement. We need to do one more thing, because what we don't know is what's going on at negative 3 and positive 3. So we have to test our endpoints. And the way that we're going to do that is by plugging the numbers in and seeing if that series converges or diverges. So we'll plug in x equals negative 3. If I plug in x equals negative 3, I have the series, the sum from n equals 0 to infinity of n squared times negative 3 to the n plus 1 over 3 to the n. Well, technically, I can rewrite this as the sum of n equals 0 to infinity. So if I have n in the denominator, I can take it out, right? I can take out that negative 3, and if I have n plus 1, right, so I can do n squared, just like I did in the ratio test. We can have negative 3 to the n times negative 3 over 3 to the n. Well, then these things right here, I can actually put those together. So I have the limit, I'm sorry, no limit, wrong problem. The sum of n equals 0 to infinity of n squared times negative 3 over 3 to the n times negative 3. Well, negative 3 over 3 is just negative 1. So that's n equals 0 to infinity of negative 1 to the n times n squared times negative 3. Well, according to our limit, our nth term test, this diverges because the limit as n approaches infinity of that term, of this thing right here, is not equal to 0, right? It'll go off forever and ever and ever. And it is, so this would be the, well, you could argue, sorry, this would not be the nth term test. This would be the alternating series test because negative 1 to the n is your alternating series. So we're left with negative 3 times n squared, which diverges because it goes off to infinity. So this will diverge, which means this is not going to be included. Okay, x equals 3, x equals negative 3 is not part of our interval of convergence. But that's just negative 3. So essentially, we're doing the ratio test again to figure out what the x values would be between. Then you're testing the end series to see if they work using another test, right? So you're not going to use the ratio test again. You're going to manipulate it so that it looks like an eyeball test and then go from there. So again, with 3, n equals 0 to infinity of n squared 3 to the n plus 1 over 3 to the n. Well, that's the same thing as n equals 0 to infinity of n squared and then 3 to the n times 3 over 3 to the n. Those cancel. We get the sum from n equals 0 to infinity of 3n squared, which also diverges. Okay, and this one would be the nth term test because the limit does not equal 0, which means that this is what we're trying to get at. That's the answer. That is the interval of convergence. So the interval of convergence, if I write this out, is the interval from negative 3 to 3. And then the radius is just 0. I'm sorry, it's 3, not 0, because the center is 0. The center is 0, so the radius is 3. When we did the last example, our interval was from negative 3 to 3. Well, if I were to write that, we knew that the absolute value of x over 3 had to be less than 1, right? And if we want it to look like this, which we do, because this is your absolute value equation, x minus the center equals the distance, right? And if you don't remember, we definitely did that concept. We learned that concept in Algebra 2. We were talking about solving absolute value equations in the real world. Well, that means that your r value is here, your center is here, which makes this very simple to solve. So you don't actually have to keep going when we're solving all the way to where you split up your equation, right? To be we got negative 3 or we said it was -1 less than x over 3 less than 1, right? We did that. You don't have to go that far. You can just leave it like this. Now the thing is, we don't want it to be divided by anything. So in our case, in that last example that we did, we would multiply everything by 3. So it would be the absolute value of x is less than 3. So our center was 0 because there's nothing being added to x or subtracted, and our radius was 3 because that's what's on the right side of the equation. The same thing happens somewhere in this example that you see in front of you. So it's x minus 3 over 2 is less than 1. That's what they ended up with, right, whenever they did the ratio test. This is what we get from that problem. Well, then if I multiply by 2 on both sides, then it eliminates the 2 here. So that means that x minus 3 is less than 2, so the center is 3. Again, inside opposite, right? Inside horizontal inverse. And then the radius is 2. So that means that your center is at 3. So if you were to illustrate this, you would get this picture right here. Right? So then starting at your center, it's to the left 2 and then to the right 2, which really is your absolute value equation. And then of course you do have to test your endpoints just like we did in that example to see if they will be included or not. Right? There's no way to know without testing them. We cannot assume.